In this video, we will practice with some formulas. This example, we have a parallelogram with base 25 feet and height of 18 feet. To find the area, we know A equals B times H. So 25 times 18. And evaluating this, we get area of the parallelogram is 450 square feet. For this example, we want to find the area of the given trapezoid. So let's write that formula down real quick. Now let's label the two bases, B1 and B2, and also the height H on the diagram. Then we just plug in and evaluate. And we end up with the area being equal to 90 square inches. Another example. Here we want to find the value of x on the triangle. To do this, we need to figure out this missing piece using the Pythagorean theorem. Now let's plug in our known values so we can solve for the side B. Getting b squared by itself by subtracting 576 from both sides. Then we use the square root property to find the value of b. And we get 45 for the side B of the right triangle. Now we can figure out what x is with this information. So let's label the base x plus 45, then use the information and plug into the area of a triangle formula, 1/2 base times height. Distribute to get rid of parentheses. Subtract 600 to isolate 24x, then divide by 24 to get x by itself. And I am silly and forgot to put the 1/2 in front of the formula, so let's do that real quick. After fixing my mistake, we end up with x equal 2. Now, we will look at converting from degrees to radians, and radians to degrees. Radians are how we usually look at angles in math. To convert from degrees to radians, we simply multiply the angle in degrees by pi over 180. So let's do this for these examples. Here, just multiply by pi over 180 to 45 degrees and simplify the fraction to get pi over 4. For this example, we do the same as above. Multiply 150 degrees by pi over 180 to convert to radian measure. After simplifying the fraction, we end up with 5 pi over 6 radians. Then we convert 85 degrees to radian measure by multiplying by pi over 180. Simplifying, we get 17 pi over 36 radians. Whoops, forgot about example C. Converting negative 270 degrees to radians by multiplying by pi over 180. We get negative 3 pi over 2 radians. Now let's take a look at some trigonometric function values for radian measure. At first, it may be easier to convert them from radian to degrees by multiplying by 180 over pi, but eventually you'll remember common values. So pi over 6 radians is 30 degrees. And we can look at some common values for trig functions on the left to see we get root 3 over 2. Next example, we can do a similar process. For now, convert radian to degrees, and we get 120 degrees. Now let's draw a diagram to help us here. Draw 120 degrees, and notice we can reference that to angle 60 degrees, or pi over 3. Then we can look at our common trig values to see it is root 3 over 2. Also remember that sine correlates with y, and in this case is in quadrant 2 and also above y-axis, so is positive. Next example, we want to find what cosine of negative pi over 4 is. Converting to degrees, we see that 45 degrees below x-axis on this diagram. Looking at our common trig values, we see that it is root 2 over 2. It's also positive since cosine corresponds with x. Note that if we wanted to find sine negative pi over 4, the result would be negative root 2 over 2, since the angle is in quadrant 4 and sine corresponds to y. For this example, similar process. Let's convert to degrees by multiplying by 180 over pi. Then let's draw a diagram to help. So negative 270 degrees goes clockwise, and we end at the y-axis, splitting up quadrant 1 and quadrant 2. If you remember when we talked about the unit circle and definition 1 of the trig identities, you can see that sine is y over r, and at the y-axis, y is 1 and radius is 1. So sine of negative 3 pi over 2 will just be y over r, so 1 over 1. Not sure why I have negative 1 here. Let's erase that and put the right answer down. Last example, same process. Let's convert to degrees, and we get 7 pi over 3 is 420 degrees. Now let's draw a diagram. So 420 degrees goes around once, then an extra 60 degrees, so we can use that as a reference angle. Using the 60 degrees as a reference angle, we then can see from our common trig values that cosine 7 pi over 3 will be equal to 1/2. In this example, we want to find all the angles that satisfy cosine theta equal to ratio of negative 1/2. Let's draw a diagram to help us out. I am drawing a unit circle with radius 1, with some key angles to help us figure this out. Now let's label some angles in degrees and radians. I'm going counterclockwise, so the angles will all be positive. So now remember some key values of our trig functions, like cosine of 60 degrees is 1/2. We want negative 1/2, but we can use this fact to help. Again, we want cosine theta being equal to negative 1/2, but we can draw what that would look like compared to 1/2. Drawing a triangle, we can see that the angle will be 60 degrees from 180 degrees, so 120 degrees, or 2 pi over 3. So for starters, we now know that on the unit circle going around once, we have cosine of 120 degrees, or 2 pi over 3 radians, gives ratio of negative 1/2. But notice, if we add 360 degrees, or 2 pi radians, we end up in the same place. This means we can have many angles that give our desired result. So we write theta equals 120 degrees plus 360 n, where n is an integer, or 2 pi over 3 plus 2 pi times n. This can also be denoted as the following. We will discuss this notation more a little later. Now let's play with an example. Here we have a triangle with some missing stuff. We want to find all that missing stuff. First, notice we have two angles and theta. We can find theta by subtracting 120 from 180, since triangles add up to 180 degrees. Then, we just need to find B and C. Let's label the triangle according to opposite, adjacent, and hypotenuse to help us out. To find B, we can use the fact that tangent theta is opposite over adjacent. To find C, we can use sine theta is opposite over hypotenuse. Now we just solve our equations for their variable B and C. Multiplying the first equation by B on both sides, then dividing by tangent 60, we get B. Using our common trig values, we know tangent 60 is root 3. So our result is 9 over root 3. Now the other equation to solve for C. Multiply both sides by C, then dividing both sides by sine 60, we have what C is. After simplifying and rationalizing the denominator, we get 6 root 3. Note, we can also rationalize the denominator for our previous result as well.